What if I told you that, as you're watching this right now, you could board a spaceship, head off from Earth in a perfectly straight line indefinitely, and you might never encounter the universe's edge? Or perhaps you would. You could possibly crash into some sort of cosmic barrier where space and time just cease to exist. Or here's the most bizarre possibility of all. Maybe you journey for billions of years only to somehow arrive back at your starting point, gazing at Earth once more. This isn't science fiction. It could be the most profoundly puzzling, unsolved question in all of astrophysics. And by the time this video ends, you'll grasp it better than 99% of people on Earth. If this video expanded your mind even slightly, please do me a favor and hit that like button immediately. It seems straightforward, but it truly helps get this video in front of more inquisitive people like you who are captivated by the universe's enigmas. But before we try to tackle what's at the universe's edge, we have to begin with a question so basic you've likely never even considered asking it. Why does the night sky appear dark? Now, I know what you're probably thinking. That's obvious. The sun isn't illuminating your side of the planet, so you perceive the blackness of space dotted with a handful of stars. But hold on, think more deeply. If the universe were infinite and packed with stars, and if it had been around eternally, then regardless of the direction you gaze, your line of sight ought to eventually strike a star. Every spot in the night sky should be ablaze with brightness. The whole sky should shine as intensely as the sun's surface. No dark areas at all, just overwhelming light from every angle. But that's not what we observe, is it? We gaze upward and see blackness speckled with small specks of light. So what does this imply? Does it suggest the universe isn't infinite? Does it indicate there's actually an edge somewhere out there? A limit where the stars simply end? This riddle is known as Olbers Paradox, after a German astronomer, and unraveling it will lead us through some of the weirdest concepts in contemporary physics. And I assure you, the resolution is way more astonishing than you anticipate. Let's return to the start. Not the start of this video, but the start of it all. Some 13.8 billion years ago, our universe burst into being in what we term the hot Big Bang. In that instant, everything was inconceivably hot, incredibly dense, and expanding at a ferocious pace. And here's the crucial point. That expansion hasn't ever halted. It's continuing right this moment. Space itself is stretching, becoming bigger with every passing second. Now, when astronomers direct their telescopes toward far-off galaxies, they observe something odd. The more distant a galaxy is, the quicker it seems to be receding from us. And if you take this concept to its limit, you reach something genuinely peculiar. What if there exist galaxies so extraordinarily remote that they're receding from us quicker than light speed? I know what you're thinking. Wait, nothing is allowed to go faster than light. You're completely correct. Nothing can move through space faster than light. But here's the mind-twisting part. Space itself is free to expand at whatever speed it desires. The restrictions don't apply to space itself. And due to this, there's a boundary surrounding us, a sphere past which everything is speeding away from us faster than light can propagate. This boundary goes by a name. It's called the Hubble sphere, and currently it lies roughly 14.4 billion light-years distant from us in all directions. Light released by anything past this sphere will never arrive here. It's akin to sprinting on a treadmill speeding faster than your running pace. No matter your effort, you lag behind. But here's where it becomes even more astounding. And I need you to focus closely, since this is the section most folks misunderstand. The Hubble sphere isn't fixed. It's enlarging every day. It grows a bit larger. And thanks to this enlargement, light emitted billions of years back by galaxies once outside the Hubble sphere can in fact arrive at us now. The sphere has expanded sufficiently to encompass that old light, which, after journeying billions of years, finally gets to Earth. We can in reality observe galaxies presently receding from us faster than light. Let that settle in for a second. This forms what we refer to as the observable universe. It's all we could ever possibly detect, everything that's had an opportunity to dispatch light our way. And it's 93 billion light years across. Now, you may be asking, wait, if the universe is merely 13.8 billion years old, how are we able to see something 93 billion light years distant? The explanation is expansion. Space has stretched the whole time, transporting that light with it. So now, we can at last resolve the paradox. Why is the night sky dark? Because as galaxies recede from us, the light they release gets stretched. It shifts toward the spectrum's red end. The quicker their motion, the greater the stretch in the light. Ultimately, it stretches enough to turn into infrared light, which human eyes can't detect. The universe is radiant with light from remote galaxies, but it's invisible to us. Thus, night's darkness actually conceals a chorus of ancient light we can't sense. But here's the key. The observable universe isn't the limit of everything. It's far from that. There's very likely far more universe past what we can detect. The issue is, what form does it assume? And this is where matters turn truly breathtaking. You might suppose the universe resembles a massive sphere. After all, if the Big Bang began at one point and expanded outward, wouldn't it naturally create a huge ball? That's what ancient philosophers such as Aristotle and Plato thought. But our data paint a different picture. And we owe Albert Einstein for explaining why. General relativity reveals that space isn't merely a flat, vacant grid. It's a curved fabric. Mass and energy bend this fabric, producing what we feel as gravity. And this principle holds for the universe overall. On the grandest scales, space-time itself can curve in one of three manners. The first is positive curvature. Picture the universe like a sphere's surface, but in higher dimensions. In this space, if you launched two parallel light beams, they'd ultimately converge and intersect, much like longitude lines on a globe meeting at the poles. In such a universe, flying your spaceship straight long enough would loop you entirely around, returning you to your origin. No edge, just an infinite loop. The second is negative curvature. Imagine a saddle shape. In this setup, parallel light lines would diverge, spreading ever farther apart indefinitely. The universe would stretch outward infinitely, never looping, never concluding. The third is perfectly flat space-time. No positive curve, no negative, just flat. Here, parallel lines remain parallel eternally. They neither meet nor diverge. They simply continue into infinity. So which one is it? How do we determine our universe's shape? Cosmologists employ a remarkably smart technique. They rely on triangles. In positively curved space, a triangle's angles sum to over 180 degrees. In negatively curved space, under 180 degrees. In flat space, precisely 180 degrees. By examining patterns in the cosmic microwave background, which is basically a frozen image of light remaining from the Big Bang, scientists measure these angles for our universe. And the findings are clear. Our universe seems flat, perfectly, exactly flat. Now, you've navigated the tough section. You comprehend that space-time looks flat on the biggest scales we can probe. But what does this really reveal about everything's actual shape and extent? Here's one option. What if our observable universe is merely a minuscule patch on a vastly larger curved expanse? Consider standing on Earth. It looks flat nearby, doesn't it? Yet we know it's a sphere. We're simply too tiny to notice the curve. Perhaps something similar occurs with the universe. Maybe the observable portion is so small a fraction of the whole that we can't sense the curvature. If so, the full universe would need to be at least 1,000 times bigger than what we observe. But today, most cosmologists favor something even more extreme. They think the universe is genuinely infinite, not just hugely vast, but literally infinite, extending endlessly in every direction with no termination, no edge, no limit. Just space, galaxies, and stars continuing forever. And this is where it becomes truly unnerving. If the universe is really infinite, then mathematically, everything has to repeat. Consider it. Everything around you, including you, consists of a finite particle count arranged in finite configurations. With infinite space packed with identical ingredients obeying identical physics laws, statistics requires that somewhere the same configuration recurs. There could be another Earth somewhere, another you. In fact, infinite versions of you could exist, some identical, some with minor differences. Perhaps there's a you viewing this very video now, but in that universe, you choose not to subscribe. Whereas here, naturally, you'll subscribe, correct? I realize this feels like outright science fiction. It likely doesn't feel right intuitively, but this is precisely what infinite universe mathematics forecasts. An exact duplicate of you would reside in a galaxy about 10 to the power of 10 to the power of 29 meters distant. That's a 10 followed by 100 billion trillion zeros. a figure so immense it's practically infinity. Yet in a truly infinite universe, you'd theoretically be able to reach it. Except you can't. And this leads to perhaps the most eerie insight of all. Recall the Hubble sphere, that limit where beyond it, everything races away faster than light. Even with a spaceship at 99.99% light speed, you'd never overtake anything past that limit. They're receding too rapidly. The cosmic speed cap has confined us. Right now, 94% of galaxies visible in our observable universe lie beyond the Hubble sphere. We detect their ancient light, but we can never visit them, never communicate, never encounter potential aliens there. They're eternally inaccessible. And it worsens. Each second, additional stars cross this cosmic horizon, turning permanently unattainable. 60,000 stars every second. Since this video began, over 50 million stars have vanished beyond recovery. 50 million stars humanity can never access. Regardless of future tech, no matter how many billions of years we endure, in 100 billion years, every galaxy save our local group will be too remote to reach. And in 2 trillion years, they'll be so far that we won't even see them. The stunning cosmic web of galaxies, nebulae, distant clusters, all will vanish from sight beyond an event horizon, as if devoured by a cosmic black hole. No matter how advanced future telescopes, humans pointing them skyward will encounter only silence and void. Picture humans evolving on a planet 2 trillion years hence. They'd gaze up and see solely their home galaxy amid endless emptiness. They'd have no clue billions of galaxies once crowded the cosmos. They'd never uncover the Big Bang, never grasp cosmic evolution. They'd likely conclude the universe is static and eternal, just their isolated galaxy adrift in infinite void, with no means to learn differently. Now, I know this seems bleak, but here's my perspective. Our galaxy alone holds hundreds of billions of stars. We haven't yet mastered leaving our solar system. The closest star is over 4 light years away, and we lack means to reach it. We have ample space to expand, countless mysteries to unravel, endless wonders to explore in our local cosmic area. And here's the loveliest aspect. You, right now, in this instant, comprehend the universe's true scale, shape, and destiny better than any astronomer from just 100 years past. The brilliant minds of the early 20th century knew none of this. You hold knowledge Einstein himself lacked. That's extraordinary. So what have we discovered? We inhabit an infinite, flat universe accelerating its expansion. No edge, no wall, no barrier ending space. Just boundless cosmos extending every way forever. Other U's likely exist somewhere in space's mathematical infinity. But universal expansion has trapped us in this small, reachable bubble. Most of the observable universe already lies beyond reach. And each second, more escapes forever. But don't grow too settled with this view. Humanity will keep exploring, discovering, challenging knowledge limits. In 50 years, cosmologists might review what I've shared and chuckle at our limited understanding. That's science's wonder. Every answer spawns new questions. Every finding unveils profounder mysteries. After all, the universe isn't required to make sense to us. Yet, against all odds, we've deciphered quite a bit about our odd cosmic abode. We're dust specks on a small planet circling a typical star in one galaxy among trillions. And we've unraveled infinity's shape itself. If that doesn't inspire awe, I don't know what could. Click the next video and join me as we plunge into even more incredible mysteries from the cosmos's remotest reaches.